Okay, welcome to this session. And today's session will focus on a symmetrical component as well as analysis of unbalanced fault in power system. So when we are talking about a symmetrical fault, we'll use a concept of symmetrical components, where a symmetrical component definition is that any unbalanced three-phase set of voltage or current can be represented as the sum of three balanced sets called symmetrical component. So when we are using symmetrical component, the basic concept behind is that for a symmetrical component, the three-phase voltage and current will be asymmetrical. They don't have the same magnitude, the same phase sequence, or similar phase difference. So such signal can be converted to a set of symmetrical component called positive sequence, negative sequence, and zero sequence. So for a balanced three-phase, the voltage magnitude and the phase sequence is now. But when the system is subjected to unbalanced disturbance, there will be unbalanced voltage and current in the power system. So this unbalanced three-phase system can be converted to a three-phase symmetrical component so that the three-phase symmetrical component can be added up together to give back the symmetrical three-phase system. So for example, we have original phase sequence of phase A, B, and C. So the sequence is phase AB. When we convert that into symmetrical component, we can have three types of a sequence where the positive sequence have the same phase sequence as the original phase sequence of a signal with the same magnitude and the 120-degree phase difference. So for example, here we have V, A, B, C, and in positive sequence also we have a V, A, B, C phase sequence, and the phase difference also 120, but the phase rotation is similar to the original signal. So we have ABC in the positive sequence. The magnitude of 3 ABC is the same, and the signal is rotating in the same sequence as the original signal. But when we come to a negative sequence, the phase sequence will be distorted. Here it is converted back to ACB. So here we'll get phase C after phase A, but it's also rotating in opposite direction. The phase sequence is in opposite direction, and magnitude is the same, whereas the displacement between a phase sequence is also 120. So if we have ABC sequence, it will be converted to ACB sequence, and the phase sequence difference is also opposite to the original. So here we have A, C, B, original signal is A, B, C. And the third component is what we call a zero sequence. And zero sequence is a DC component. So the zero sequence of all phases, that means phase A, phase B, have the same magnitude and the same direction. So equal magnitude and equal direction. So at any time, whenever there is a symmetrical fault, we can convert the asymmetrical component into three phases of symmetrical and three components and determinants. So, for example, the phase A can be explained as the summation of positive sequence, negative sequence, and the zero sequence for phase A. Again, phase B also can be explained as positive sequence, negative sequence, and the zero sequence of phase B, and phase C also the same. So all have similar. So the transformation between phase quantities and symmetrical component is done by using this matrix. So the zero sequence is obtained as the summation of all three phase, and taking the average of it, because we are using three phase and we divide that by three phase. Whereas the first sequence or the positive sequence is obtained as this phase A plus phase B with 100 degrees phase shift and phase C with 240 phase shift, and taking the average of that. Whereas the negative sequence is that the phase order will be distorted. So we'll get phase A, phase C, and phase B. So phase A plus this multiplier is phase B will be distorted. It becomes 240 degree, and phase C is 120 degree phase, because the phase sequence changes and we'll take again the average. So this is the expression how we can convert the unsymmetrical component to symmetrical one. So meaning zero sequence component are in phase and the magnitude is the same for all phases when there is asymmetrical fault. Whereas the positive sequence will have the same phase sequence as the original signal ABC. Whereas the negative sequence has a negative sequence component and the sequence is changed from ACB, because original signal is ABC, but it's converted about ACB. So these are again to construct the original signal BABBC. From this we multiply it with a negative of this matrix and multiply it by 3 because it's the division. So we'll get this VABBVC can be constructed from a phase sequence or symmetrical component by using this. So phase A is the summation of first sequence, second sequence, and negative sequence. Phase B will be 0 plus 120 times V1, then like this. So we obtain this. And the meaning of this A is 100 degree phase shift. And if we want to write this in a rectangular form, it has this representation. The importance of calculating the asymmetrical fault is to obtain the magnitude of the protection system required, because as we try to say earlier in symmetrical fault calculation, the maximum current that will run in a power system will occur when a three-phase fault is occurring in the power system. But what is the advantage of these asymmetrical fault? So in the case of asymmetrical fault, there will be a negative sequence current that runs through the network, and this will increase, especially the thermal limit, because it's producing a phase sequence which is reverse to the original sequence. For example, take a motor. If our system is supplying a motor, so motor is running in normal direction and the fault is occur, so our voltage will have positive sequence, zero sequence, and negative sequence. Positive sequence is trying to push a motor to run in the normal direction, whereas negative sequence will run the motor in opposite, because you know the phase reversal is used to change the direction of the motor rotation. So this creates the two opposing torque in the motor, and will create a problem, especially in the heat industry. And this is why we have to determine the magnitude of the negative sequence current and negative component that will run when the system is exposed to asymmetrical fault. So it's very useful for power system protection, unbalanced load flow analysis, and the power quality study, because the voltage balance created as one of the power problems. So this is a representation, three-phase component representation. For positive sequence will be ABC, negative sequence will be ACB, and For a zero sequence, it will have the same magnitude in the same direction. So this balanced state displaced 120 degree, same magnitude. So phase sequence is similar to the original signal, whereas for negative sequence, balanced state displays 120 degree opposite phase order. So phase will be ACB, not ABC. So that's the expression of a negative sequence. When we come to a zero sequence, it's like the average of the voltage, original voltage or filtered voltage and semi voltage, and we'll take the average. So for any unbalanced system, we'll have this formula. For example, let us see this with a numerical example. Consider this numerical example. A voltage A have 10 kilovolt at 0 degree angle. B has a 6 kV at 130. Then VC has this magnitude. So this clearly visible that our three phases have different voltage magnitude as well as the phase difference. So we can calculate a symmetrical component from this by applying this straightforward equation. V naught V1 V2, which is a symmetrical component, will be taken as the average of a 3. Then we'll add these to get their sequence, this multiplied by this. So it becomes this magnitude. So this is a 0 positive and a negative sequence. So we'll have 0.33 at angle of something, V1 7 point, and the V2 this magnitude. So we can reconstruct by applying this equation again. This equation can be used to reconstruct the original signal, and if we use this and take the calculation, it will become back to the three-phase unbalanced, which is indicates that our system. This example shows how any unbalanced three-phase set is resolved into 0, positive and a negative second component, and then we can rebuild it to get the original unbalanced. And we carry out the review of this component. Why this component is very important, why we are carrying it, and how we can employ this. Because we said that we have a positive sequence, negative sequence, the zero sequence, and that will be used for the analysis of asymmetrical fault. So we have to understand what is the meaning of those components. So this is a very simple transformation to get a balanced three-phase voltage symmetrical component. So from a symmetrical component, we can get directly this. So if you see that, this is how we can represent pictorially the meaning of this phase sequence. So sequence is positive sequence. We have VABC. So one is positive sequence, and we will have this. So VAB like that. So again, we have a negative sequence. In negative sequence, we have this signal like equal magnitude, but in different sequence. Here, it will be B and A. So this is 120 degree, and it becomes ACB. ACB is ABC, whereas their sequence is the same magnitude with phase sequence. So we can invert that to get phase sequence. It's very simple. But why we use this is finally we will apply this a sequence or what you call symmetrical component of a voltage to a sequence network so that we can analyze the magnitude of asymmetrical current under different fault conditions. For a balanced system, the sequence network are obtained by replacing all sources with internal impedance for positive sequence. Positive sequence is already, we have seen that is already replacing, we can obtain the total impedance. Again, for a negative sequence, we don't have a source that become equal with Z, which is negative sequence of component will be given. Zero sequence also don't have a source, so it becomes like that. the Z node is connected to ground. This is the meaning, is the magnitude of impedance that connect the system to the ground. So Z1, Z2, and Z are driving point impedance seen from a fault location for positive, negative, and the zero sequence network respectively. In most practical systems, Z1 and Z2 will be the same, but Z0 is very small impedance. Positive sequence and negative sequence is the same for most